Yeah, good afternoon. I'm RASMUS BENESTAD, working at the Norwegian Met Institute, and I'm going to talk about a new project called Springs. And I'm just a work package leader of this project, but I'm going to tell you what we intend to do. We just started. So it's about modeling how climate change may affect the outbreak of diarrhea, which is not a very delicate subject. But this is actually a health call, so this is more like from the health side, and we are providing some input to the health sector. So here you can see a part of the problem, why we're actually doing it, and also I will say something about our approach, how to do that. Basically, we have more heavy rainfall and temperature that affect runoff and water quality. Water quality is a big sort of keyword here. And then the spread of pathogens. And in order to understand how this happens, we have a chain of different models because there are different sectors. So you have different models. So we start off with rain and temperature, and then model, and then pathogens. But also that will be taken on to the clinical medicine, and also outbreak of cholera, but also maybe policy, and it also help water management as well. So the concept here is we're trying to improve the preparedness and resilience of the society, and through adaptation and also planetary health policies. So that's what we're aiming for. So we're quite ambitious, I would say. So we have global warming, and that leads to more extremes, and then these extremes, they will wash away all the dirt and all the tears and whatnot into the rivers, waters, and so on. And that affects both the water levels, but also the microbial water quality and water quantity. And then that leads to the hospital here. You see like waterborne diarrheal burden and also outbreaks. So that's the concept of. So just to try to sort of give like an outline of what we're going to do is that first we want to evaluate climate models. So we find that evaluation is really, really important, and that is often skipped. And you should never do that. I went through a lot of papers that had wrong conclusions, and I think has been downloaded 170,000 times. But one of the key message we had from that paper was that the papers with misunderstood conclusions, or wrong conclusions, are the ones which haven't actually done proper evaluation. And also we want to develop a downscaling method to downscale statistical properties. I'll come back to that. And then weather generator to take these statistical aspects or properties to generate time series that can be used fed into the water models. And then we want to assess the methods. In addition to the climate models, we want to assess and test everything all the time. And then we will apply this downscaling to some pilot regions, and then test results as input to the water model. And so the case studies that we are focusing on are, one is in Accra, Ghana, and here you have the climate hazards, like coastal and estuarine flooding, like storm floods and droughts. And the vulnerabilities are childhood malnutrition, unsafe water and sanitation, unplanned or urban housing, poverty, reduced access to healthcare and education. And in Tanzania, Haydam, we have flooding and droughts, and also there, childhood malnutrition, food insecurity, unsafe water and sanitation, poverty, and here you also have some animal and agricultural exposures, but maybe not animal health. But actually, animal health is also affected by this as well. And then we have Romania, Timisoara. And as here we have flooding, surface water flooding, flash flood and droughts, and then finding Naples in Italy. So 2 sites in Europe and 2 in Africa. They're quite different in Africa. I think one is north and one is south of the equator as well. So that's going to be interesting. And the problem with Africa is also that we lack observations, so it's going to be a bit challenging. So here's a model chain very, very roughly. So this is a cross-disciplinary cooperation involving various modeling stages and also co-production of knowledge. So we will be, or my group will be mostly in the climate aspect, but also water modeling as well. And then we'll also bring that to society and then understanding the society, social sciences, and medical research, and also epidemiology. Yeah, I'm a climate scientist, so I'm not using that word. So anyway, so we will focus on these two first stages in the start, and then we will of course follow the information all the way to the end. And one important thing we always should ask is, how do you use the information? And also how you have you used that information in the past? How did you intend to use this information? What do you expect from us? And we need to have a discussion because we always have different expectations. And by having this sort of dialogue, we can try to find an optimal flow of information. So here are the stakeholders. You can see there are quite a few different ones. Like we start with medical doctors who are all coordinating this, but we have disease modelers, water managers as well, and hydrologists, and also health economists as well, public health experts, biologists, and social scientists, one or two, and then also some communicators as well. And the partners is also a long list. But it's coordinated from the Netherlands. So the challenge then is, of course, to the communication aspect and understand across the disciplines. Because when I say model, somebody else have a completely different interpretation of what a model is. So we have to start with it. So what we want to do is to start with an overview and tell the story where the information comes from. So we are working on a manuscript which we call Downscaling for Medical Doctors, because they're not accustomed to this, to what we're doing, and so they should have no doubt about what is actually behind the information that they're using, and also its limitations as well. I'll say something about this actually later on. So yeah, well, you can actually see why we need to do the downscaling. This map shows the elevation of a global climate model, and you see that it's not very, very detailed. So the global climate models are not designed to provide local information. And for example, here, like you see with this sea mask here, it contains very coarse pixels. And then you can see at the bottom here is basically the problem, like on a very, very local scale. So how can you distill information from these global climate models, which are the main tools of providing indications of what we can expect for the future to this local scale. So we have the global climate models, and basically they represent the laws of physics, which describe how the temperature changes, and air flows, and the water evaporates, and the precipitation shapes our daily weather. And then the downscaling basically because the local climate depends on its large-scale ambient environment as well as the local geography, we can make use of this information and add it to what the climate models produce. And the information about this dependency between a large scale and small scale is what we add, and then this is actually what we call downscaling. So this illustration shows like what the global climate models produce, and also shows like where we want to say something about a risk about flooding, for instance. And here's also another illustration. So you see, this is the island of Sardinia, because they had lots of rain gauge data. And you can see the mean rain gauge data on different spots, and you have quite a bit of variation there. And then you see in the background, the blue rectangles. These are from climate models. So you can see that the climate model may represent like the rain gauges in one or two pixels. And actually, I apologize. We have this, so that we don't have full screen, do we? But this histogram shows like the yellow histogram is the model results, and then the gray that shows all the station data. So you see that the spread in statistics is much wider when we look at the real world than the model world. So we take the global time model and then we downscale it. What we do is actually, in this case, we want to downscale statistical properties rather than day by day. Why do we want to do that? Because the statistical properties are much more predictable than the outcome. And remember Las Vegas, right? They live because they can predict the probabilities of wins, and the statistics is very predictable, but the outcome is very unpredictable. Like nobody knows who wins and what doesn't win, right? So people get sort of attracted to it because they want to gamble, right? But the statistical properties are almost always, I don't know any case where it's not more predictable than the outcomes. And this is a very robust way of achieving the results. So, but then once we have this, and in this case, what we need to predict two different parameters. One is because we know what the rain is. Some days it does rain, some days it does rain. So then we need to know the fraction of rainy days. That's what the frequency. And then we need to look at the days when it does rain, and we see that the histogram there is actually very close to the red line, which is an exponential distribution, and we only need one parameter to describe that, and it's actually the mean of the rainy days. So that's a very easy parameter too. So we can downscale two very easy parameters, and from that we can generate daily rainfall that mimics the real world, and we can feed that into the water models, and that's what we want to do. And then we can change these statistics, and we can in a way forecast or project how the statistics change in the future, and that will also translate into more extremes, and it will also give us input to the water models for the future. So, so the information chain is estimating a local statistical properties, and these are the two parameters I talked about. And then we use these to generate random numbers. It's a Monte Carlo type of simulation to feed the water models. So of course we need to test them to make sure that they actually make useful results. But as I said earlier today, that we should never use just one way of downscaling. We should also use dynamical downscaling. So what we'll do, we'll find other dynamical downscale results available. And this example here shows that we not only do that, but we downscale like all the CMIT runs statistically, because we can do it in a few hours. So it's very quick because statistical downscaling doesn't require much computational resources, because it's based on mathematics and statistics. It's not AI, but it's a much more elegant way of doing it. But the dynamic downscale results take a lot of resources, but there's some around that we can use and compare. And here's one comparison between the temperature of 9 downscale results based on 4 global climate models. And you see the red lines are the statistical downscale for the same model. So you see that they follow each other. So we have confidence. These results are credible, and then we can use either actually. But to have this confirmation is really, really important. So, and also Springs has like impact. So like a Springs output will be the mechanistic knowledge, like how flooding will affect pathogens and also the water quantity. So this is something basically this is something we hope to learn from the whole process of the model chain. And also like surveillance tools as well is important to try to forecast when there's a flood, and also risk for flooding and health issues as well, and provide indicators and also prediction maps, and also interventions. So basically try to provide guidelines for the authorities and policies in those countries. So at least in the pilot regions. and also provide policy scenarios. So there's a group of social scientists and also economists who work on that aspect. And then also in the medium term, improved and integrated surveillance and improved prediction and preparedness for the future risks, and also interventions to improve preparedness which are prioritized based on integrated value assessments, and also involve the water companies to improve the water quality monitoring, and sustainable transdisciplinary multi-sectoral and scientific network, and also engage citizens. So the water supply systems are hopefully then made more resilient and safe, and also capacity building as well for surveillance. And then the wider impact in the longer term, basically environmental and health policies and practices will be more integrated and sustainable. And upstream determinants are understood and reduced, and also increased adaptive capacity and resilience. And ultimately, like basically deaths and illnesses are reduced as a result of this. And citizens' health and well-being is protected and promoted equally. So that's a short reference there, so you have access to the presentation. So this is like a discussion paper, and that's all I have. And this is Vanessa Harris. She is a coordinator of this project. So thank you for your attention, and if you have any questions, please don't hesitate to ask.
Thank you, Rasmus.